Now I want to briefly talk about a Fourier transform, not only for the L1 of G, but also for measures on G. So the motivation, I guess this is a recurring theme in this chapter. So we have this L1 of G is kind of embedded inside the M of G by identifying a function f with the f d, say, we just use dx for now. I know I used d mu early on, but let's use dx as the left higher measure. So every L1 function, you can identify it as a measure on G by just sending it to be the f times the left higher measure. Right, so we know this embedding is a star homomorphism, so on. So this is a nice embedding. All right, so we talk about the Fourier transform for the L1 functions. But if you think about what happens of the Fourier transform, so it basically gives you a function defined on the dual group. You evaluate your fx against the conjugate of the character. And then if you just rewrite it as the following, you rewrite it as phi x integrate against fx dx. Then this one just looks like what it is in the, if you treat your L1 of G as a measure in the M of G, this is exactly the measure you're dealing with. So essentially this tells you, well, maybe there is a more general notion of the Fourier transform on the measure group, okay? So let's do the following definition. So if you have a, say, lambda inside the M of G, all right, then you can define this Fourier transform. So is Fourier transform by essentially just replacing the fx dx by the d lambda. Okay, so by this lambda hat, again, is evaluate given a character on the dual group, evaluates to the integral of the phi bar d lambda. Okay, so this is the definition. All right, so of course, now we have this this Fourier transform defined from the g hat to the complex number. So how continuous is this Fourier transform of a measure? Okay, we know if you have an L1 function, then its Fourier transform is continuous and is in a C0 function, basically the closure of the compactly supported. So what about now I have a measure on G, so what is Fourier transform? So here's a little proposition. We're not really using it, just some nice thing to know about. So actually, if you have lambda inside the measure space, then the Fourier transform is actually inside the continuous and bounded functions on the g hat, okay? And moreover, this lambda to this lambda hat is again a contractive, by contractive I mean norm decreasing, so norm decreasing. And it's also going to be a star homomorphism, okay, star homomorphism. All right, so essentially what do you have in the L1 function? So remember your L1 function to its Fourier transform is also contractive and star homomorphism. And it's just the range is inside the C0 of G hat, okay? So now you can do the extended to this measure space, but your range is now inside the CB of G hat instead of C0, and everything else just works very similarly, all right? So I guess the proof, the hard part is really just checking is continuous, okay? The rest checking is a norm decreasing star homomorphism. You can just, I would just leave it as an exercise. Just follow the definition. It's just some purely algebraic exercise. So let's just do the following. So let's check this mu hat is actually continuous. And to show it's continuous, all right, so let's do the following. So essentially, I just want to know what's the difference between its value between two of these characters. So if I have phi1 and phi2 in G hat, let's say phi1 and phi2 inside G hat, so I basically want to know what's their difference. All right, so by definition, this is going to be equals to the integral of the phi1 bar minus phi2 bar, and then you integrate against your measure lambda. And of course, this is going to be less than equals to the integral of the phi1 bar minus phi2 bar. And then you do the absolute value. Your lambda may be a sign measure, also a complex sign measure. So you do the absolute value, all right? So just just quick reminder, this lambda, the absolute value lambda is not taking the absolute value on each set, is actually coming from the kind of the Jordan decomposition, but because you may have a complex value measure, so you do the, you first decompose it as the real part and the imaginary part. Okay, those are two measures, and then you do the Jordan decomposition. So you have the real part, you have the plus minus the negative part, and then for the imaginary one, you have the plus minus the imaginary minus, and your absolute value is essentially just summing all of these parts up. Okay, so you do the sum, you ignore the minus sign and the imaginary unit. You just do the sum of them. Okay, so this is the absolute value. So basically, you can prove that this inequality hold when you have a lambda, a complex value measure. All right, so because your lambda is need to be bounded inside this M of G, so for every epsilon greater than 0, you can find some compact set where this lambda kind of disappears outside this compact set. Okay, you can think about this lambda as almost supported on a compact set. Okay, so there exists a K compact where your integral on the K complement of your d lambda absolute value, that's going to be less than epsilon. All right, so essentially now, if you remember, the basic neighborhoods on this G hat have this form n of K epsilon. Essentially, it is those sets where two characters are close enough on this K, all right? So this is, so if you have, say, phi1 and phi2 inside this nk epsilon, then this is essentially means the phi1x minus phi2x, they're going to be less than epsilon. And of course, when you take the conjugate, it's still less than epsilon. So now you plug it in back. So this, let's just write lambda hat phi1 minus lambda hat of phi2. Now I have that's less than equals to the following. So less than equals to the integral of the phi1 bar minus phi2 bar d lambda. And I break it according to K. So I say, well, let's integrate on K, and then I integrate on the K complement. Okay, do the same thing, phi1 bar minus phi2 bar. And on the complement, well, the difference of two characters, the characters are bounded above by 1, so the difference absolute value bounded above by 2, so it's going to be less than or equal to epsilon. It's not too big. And on this K, well, because you have this inequality, the phi1 and phi2 are close enough in some neighborhood. So all of these absolute value is going to be less than epsilon. So this is bounded about by epsilon times the norm of your lambda, or think about lambda of K. Okay, so you can do lambda K, and it's bounded about by the lambda, so you just ignore the K. But anyways, this is some constant times epsilon, so this is going to basically goes to 0 as epsilon goes to 0. So what you showed is that as long as your two characters, phi1 and phi2, are in some small neighborhood, okay, some small basic neighborhood, then your Fourier transform the evaluation on these two characters are really close. Well, this is essentially, well, not only proving it's continuous, but it's actually uniform continuous, okay? So your lambda hat is in fact uniform continuous. Okay, so of course it's going to be continuous. All right, so I basically, that's all I want to prove for this proposition. The rest of it proving is bounded, contractive, star homomorphism, you can prove it on your own. Okay, those are kind of the easy part. Well, but I do want to talk slightly more about why do we care about this kind of transformation. Well, in fact, we not only interested in this Fourier transform, we're actually interested in the Fourier transform of the measure space on the dual group, all right? So suppose you have, say, G is locally compact abelian. Well, then immediately we have this dual group is actually also locally compact abelian, all right? So if I consider some, let's say, row inside the M of your G hat, all right? So what you can do is you can define something like a Fourier transform, all right? So, well, not to the double dual, in fact, it's going to be the double dual by the Pontryagin duality, but for now we don't have it, so let's just write a formula down for now. Okay, if I want to evaluate at some x inside G, I do basically the same thing. I integrate all these d row of phi, and then I evaluate phi x. Well, that's going to give me a function on G now. Okay, well, technically, I should say the Fourier transform of this phi go to the continuous function on the double dual group. Okay. But let's just keep this function as a function on G for now. All right, so now we have a proposition. So in fact, this map is going to be really important in the next theorem we're going to talk about. So I just want to show several things. So first of all, this function is, again, a bounded continuous function. So it's from G to C is going to be bounded and continuous, all right? And also I have something similar, the this mapping row to this file row. So essentially your row is inside the measure space of the dual group, and you map it into a continuously bounded function on the G hat. Sorry, not G hat, but on G. Well, this map is also going to be contractive linear, so star linear. Okay, so it's going to be contractive and linear. And not only that, this map is actually just injective as well. Okay, and injective. So injective means if phi row is going to be 0, then row itself has to be 0. Okay. So the contractive linear, again, those are kind of the easy part. You can just check. I shouldn't say linear. I should also say it's a homomorphism. But anyways, let's just prove the injective part. Okay, so this is really the key part. That's only the non-trivial thing. So to prove the injectivity, so if I have, say, 5 row, it's going to be equal to 0. So what it means is that for every f, well, think about phi row as continuous function on G. Well, any continuous function on G is, of course, in the L infinity. So you can treat it as the dual of the L1 space. So if that's going to be equal to 0, then you integrate against the L1, then you always have 0, okay? So for every f inside the L1 function, then what you have is the following. So for every f, if you integrate the fx with the phi row of x, okay, dx, okay, that's going to be 0, right? So that's by definition. All right, so now let's expand this. Well, this is expanded phi row, so this is just the double integral of the fx, and the phi row is no other than the phi of x d of the row phi. Okay, row is the measure on the dual group, and then you do the dx, the left-hand measure on G. Well, now if you look at this, if you integrate against the x first, all right, so let's switch the order of the integral. So if I integrate the fx, phi of x, dx, and then I do the row of phi, all right, then you realize, well, whatever is inside here looks like a Fourier transform of the f, okay? It's not a Fourier transform evaluated phi, but actually at the phi inverse, okay? So because here I don't have a conjugate over the phi, so this is essentially the Fourier transform of f evaluated at phi inverse, all right? So I have the integral of that is always equals to 0, okay? Well, but the Fourier transform of your function, of an L1 function, we know is dense inside C0, okay? So the Fourier transform of the L1 of G is sitting inside the C0 of the G hat and is dense. Because this inclusion is dense, then if you integrate any C0 function against this measured row, you get something 0, and well, that can only happen when your row is the 0 measure, okay, because of the Riesz representation, essentially. So you have row has to equal 0, okay, so this proves the injectivity